For millions of years, our ancestors walked the earth. But they were being chased. Not by predators, not by enemies. They were being chased by the sky itself. Everything you learned about human evolution started with a mistake. And that mistake might be the most important thing you've never questioned. Picture the story you were taught in school. Africa dries out. Forests retreat. Grasslands expand. Our ape-like ancestors come down from the trees, stand upright to see over tall grass, and begin their journey toward becoming human. It's clean. It's logical. It's wrong. For nearly a century, scientists believed this narrative, what we call the Savanna hypothesis. Raymond Dart proposed it in 1925 after discovering the Tong child, a 3-million-year-old skull with both ape and human features. He looked at Africa's expanding grasslands and thought, this is it. This is what made us human. Walking upright to see predators in the grass, freeing our hands to carry tools across open plains, developing big brains to navigate the savanna. The problem? Every single piece of that story falls apart when you look at the evidence. The earliest bipedal hominins, creatures like Ardipithecus ramidus, walking upright 6 million years ago, lived in wooded environments, not grasslands, forests. Ororin tuganensis, another early bipedal ancestor, inhabited forests. So did Australopithecus afarensis. Lucy, perhaps the most famous early human ancestor, lived 3.2 million years ago in a mosaic of woodland and grassland, not the open savanna the old theory required. And here's what shatters the savanna hypothesis completely. Bipedalism evolved roughly 4 million years before stone tools. 4 million years. Our ancestors were walking upright long before they needed to carry anything. But the most damning evidence comes from what happened to the specialists. At sites across East Africa, paleontologists have found the bones of animals exquisitely adapted to grasslands. Giant grass-eating baboons called Therapithecus oswaldi, weighing over 127 pounds, with massive teeth specialized for grinding tough grass. Zebras with towering grass-shearing teeth, specialized grazers built for the savanna. They all went extinct. The survivors? The flexible ones, the omnivores, the baboons that could eat many foods, not just grass, the zebras that could graze and browse, the species that weren't perfectly adapted to any single environment. If the savanna made us human, why did the savanna specialists die? There's a deeper story here, a stranger story, and it changes everything about what we are and what we might become. The answer is buried in the hills of southern Kenya, in a place where the earth keeps meticulous records. "90 kilometers southwest of Nairobi, in Kenya's Great Rift Valley, there's a prehistoric site that has preserved something extraordinary. Not just fossils, not just stone tools, a chronicle of chaos. The site is called Olorgesailie, and if you stand there today, the landscape tells you nothing about what it once was. It's hot, dry, dusty. Temperatures hit 104 degrees Fahrenheit, sparse vegetation, rocky outcrops. But walk those hillsides, and you'll see something remarkable in the sediment layers. Lake deposits, then volcanic ash, then drought-cracked earth, then lake deposits again. Back and forth, back and forth. A rhythm of catastrophic change stretching across more than 1 million years. Dr. Rick Potts, a paleoanthropologist with the Smithsonian's Human Origins program, has been working at Olorgesailie since the 1980s. When he first arrived, He believed the Savanna hypothesis. He was looking for evidence of how our ancestors adapted to expanding grasslands. What he found instead was a landscape that wouldn't stay still. "I walked up and down those hillsides," Potts would later recall, "and I saw in the rock record a large lake stretching across the basin. Then the lake was gone. Then a volcanic eruption. Then the lake was back. Then severe drought. Then the lake returned." This wasn't a stable environment trending in one direction. This was environmental whiplash on a geological scale. But Olorgesailie had a problem. A gap. A frustrating, tantalizing gap in the story. For 700,000 years, the people living at Olorgesailie made hand axes, large oval stone tools used for cutting, scraping, butchering. Generation after generation, the same tools, the same technology, no major changes. This period is called the Acheulean, and it represents one of the most stable technological traditions in human history. The last hand axe at Olorgesailie dates to 499,000 years ago. Then, nothing. Erosion had stripped away 180,000 years of sediment. When the record picks up again at 320,000 years ago, everything has changed. The hand axes are gone. In their place, smaller, more sophisticated tools, projectile points, scrapers, awls, evidence of long-distance trade networks, color pigments suggesting symbolic communication. Different tools, different behaviors, different minds. Whatever happened in those missing 180,000 years transformed our ancestors from one kind of creature into something else entirely. Potts and his team needed to recover that lost time. They needed to know what environmental forces drove that transformation. In September 2012, they brought in a drilling company. 20 kilometers south of the archaeological sites, in a flat, grassy valley called Kura, the team drilled into the earth. They had no guarantee what they'd find. Maybe just volcanic ash. Maybe nothing useful. For weeks, the drill went down and down, through sediment that hadn't seen daylight in 500,000 years. 139 meters. In some locations, 216 meters, reaching all the way to the floor of the Rift Valley. In April 2013, an international team of 32 scientists gathered at the University of Minnesota's National Lacustrine Core Facility. Before them, 2,400 core samples, segments of ancient lakebed, volcanic ash, fossilized pollen, diatoms, charcoal. Each layer a page in the climate record. What they found in those sediments was stunning. For the first 600,000 years of the record, the environment at Olorgesailie was relatively stable. Freshwater lakes, wooded grasslands, grazing zebra, rhinoceros, baboons, elephants. A predictable ecosystem that supported the slow, methodical production of stone hand axes. Then, around 400,000 years ago, right in that missing gap, something changed. The climate began to oscillate wildly, wet periods alternating with extreme droughts, forests giving way to grasslands, giving way to near desert, giving way to forests again. The frequency and amplitude of these swings increased over hundreds of thousands of years. The fossil record shows that more than 80% of the large mammal species at Olorgesailie went extinct during this period. The specialized grazers disappeared. In their place came smaller, more flexible species, animals that could eat many foods, animals that could tolerate wider ranges of temperature and rainfall. And in that same period, the Acheulean hand axe tradition, stable for 700,000 years, vanished, replaced by innovation. This wasn't evolution adapting creatures to a new environment. This was evolution adapting creatures to change itself. What makes a species successful? For most of Earth's history, the answer seemed obvious. Specialize. Become exquisitely adapted to your environment. Polar bears for ice, camels for desert, rainforest sloths for canopy. The better adapted you are to your niche, the better you survive. But there's a hidden assumption in that thinking, that the environment stays put. Rick Potts looked at the extinction patterns in East Africa and saw something that didn't fit the old models. The specialists were dying. The generalists were surviving. And this pattern repeated across different animal groups during periods of rapid climate fluctuation. He proposed a radical idea: variability selection. The hypothesis goes like this. When environments change slowly and predictably, specialization wins. But when environments become unstable, when selection pressures reverse direction frequently, what survives is not adaptation to any particular environment, but adaptability itself. Not strength for the grassland or the forest, strength for change. We are, quite literally, the children of chaos. Between 800,000 and 200,000 years ago, Earth's climate fluctuated more intensely than at any other period in human evolutionary history. This wasn't subtle. These were ice ages, alternating with warm periods on cycles of 100,000 years, overlaid with shorter cycles of 41,000 years and 23,000 years, driven by wobbles in Earth's orbit and axis. The northern ice sheets advanced and retreated. Sea levels dropped by more than 300 feet during glacial peaks, then rose again. Rainfall patterns shifted. Entire ecosystems transformed within generations. And during this exact period, the period of maximum climate chaos, something extraordinary happened to the human brain. For the first 4 million years of hominin evolution, brain size increased very slowly. Australopithecus afarensis, our 3.2 million-year-old ancestor Lucy, had a brain of about 450 cubic centimeters, similar to a chimpanzee. For millions of years, brain size hovered around that number. Then, 800,000 years ago, the graph changes. Brain size begins to accelerate dramatically. By 200,000 years ago, the emergence of Homo sapiens, the average human brain had reached 1,350 grams, more than triple the size of a chimpanzee brain. The correlation is undeniable. The greatest increase in brain size corresponds precisely with the greatest increase in climate variability. A large, complex brain is expensive. It consumes 20% of the body's energy, while representing just 2% of body weight. That's a massive metabolic cost. Evolution doesn't invest in expensive organs unless they provide a survival advantage. In a stable environment, that cost might not be worth it. But in an unpredictable world, a brain capable of learning, problem-solving, innovating, planning for multiple possible futures, that brain is survival itself. Variability selection doesn't produce specialists. It produces versatilists. And you can see it in the fossil record. Bipedalism, walking upright, evolved around 6 million years ago. But here's what's fascinating. For millions of years after that, our ancestors maintained the ability to climb trees. Their shoulder joints, their foot structure, their hand proportions, all showed that they could walk efficiently on 2 legs and still climb when needed. This isn't perfect adaptation to the ground. This is keeping your options open. Stone tools show the same pattern. The earliest tools, dating back 3.3 million years, were simple. Rocks shaped to have a sharp edge. For hundreds of thousands of years, the tools barely changed. But then, at Olorgesailie, beginning 320,000 years ago, there's an explosion of innovation. Projectile points that could be hafted to spears, hunting at a distance. Scrapers of different sizes for different tasks. Awls for piercing hide. Tools made from obsidian imported from 25 to 95 kilometers away in multiple directions. That obsidian is key, because obsidian doesn't exist at Olorgesailie. Someone had to know where to find it. Someone had to travel there or trade for it. This implies social networks, communication across distance, exchange systems. And with those obsidian tools, archaeologists found something else. Pigments. Manganese for black, ochre for red. Rocks deliberately collected, ground into powder. We don't know what they colored with those pigments. Bodies, weapons, symbols on hides. But we know what color does for humans. It signals identity, belonging, alliance. These people, 320,000 years ago, were creating meaning. They were building networks of cooperation that extended beyond their immediate group. They were using symbols. They were becoming us. At Olorgesailie, the environmental instability that began 400,000 years ago didn't kill the inhabitants. It made them more innovative, more social, more adaptable. The chaos didn't destroy them. It made them human. Evolution is not a story of progress. It's a story of trade-offs. And the human brain, that magnificent, oversized, energy-guzzling organ, required sacrifices. Anthropologist Leslie Aiello and evolutionary biologist Peter Wheeler proposed what they called the expensive tissue hypothesis in 1995. The logic is elegant. If the brain grows and the brain consumes so much energy, something else has to shrink. The gut. Humans have remarkably small digestive systems for primates of our size. Chimpanzees, gorillas, they have long, elaborate intestines to process tough plant matter. We don't. Our guts are shorter, simpler. Though some scientists now suggest it wasn't just gut for brain. Perhaps we traded muscle mass. Perhaps we evolved to carry more body fat as an energy buffer. The metabolic accounting is still being tallied. But one thing is clear, something had to give. And something had to change about how we ate. Anthropologist Richard Wrangham argues that cooking was the breakthrough. Cooked food is easier to digest. It yields more calories for less gastrointestinal work. Soft, cooked tubers and meat deliver energy efficiently to a smaller gut, freeing up metabolic resources for the brain. When did humans start cooking? The evidence has been assembling piece by piece. Sites like Wonderwork Cave in South Africa hinted fire use as far back as 1 million years ago. At Geshe Benot Yaakov in Israel, scientists found the remains of roasted fish, direct evidence of cooking 780,000 years ago. And in 2026, researchers in Britain confirmed something remarkable. Humans weren't just gathering fire, they were making it. At Barnum in Suffolk, evidence shows deliberate fire-making 400,000 years ago. By 300,000 to 400,000 years ago, regular hearths appear across multiple sites. Systematic cooking had arrived. Right in the window when brain size was accelerating. There's another cost to the big brain. Time. Human infants are helpless for years. Our brains are so large that we're born early, before the skull hardens too much to pass through the birth canal. Then we spend years learning. Years depending on adults for food, protection, knowledge. This extended childhood requires cooperation. Grandmothers, fathers, aunts and uncles. Humans are the only primates where males regularly provision offspring and where postmenopausal females play active roles in child-rearing. The brain didn't just change our heads, it changed our families, our communities, the entire structure of how we live. By 100,000 years ago, the genus Homo had diversified into at least 5 or 6 species living simultaneously. Homo sapiens in Africa and the Middle East, Homo neanderthalensis, Neanderthals, in Europe and Western Asia, with brains even larger than ours in absolute size, though with different proportions, robust builds, stocky frames adapted for Ice Age cold. Homo floresiensis in Indonesia, the so-called hobbits, small-bodied with brains around 380 cubic centimeters, yet capable of making sophisticated tools. Homo luzonensis in the Philippines, another island dwarf, small like the hobbits, surviving until perhaps 50,000 years ago. And remnants of an ancient lineage, Homo erectus, still holding on in Southeast Asia, the last survivors of a species that had walked the Earth for nearly 2 million years. And based on DNA from a cave in Siberia, Denisovans, a ghost population we know almost entirely from genetics. We have only fragmentary bones, but their DNA tells us they ranged across Asia, even adapting to the thin air of the Tibetan plateau. Modern Sherpas carry their high-altitude genes today. All of these species were human. All were intelligent. All had culture, tools, fire. And now, only one survives. Us. What happened? For decades, the story was simple. Homo sapiens left Africa around 50,000 to 60,000 years ago, spread across the world, and outcompeted everyone else. But new evidence is complicating that story. DNA analysis published in 2024 shows that humans and Neanderthals interbred multiple times, first around 250,000 years ago, then again around 100,000 years ago, and finally around 45,000 to 50,000 years ago. Modern non-Africans carry about 2% Neanderthal DNA. Many people of Asian and Pacific descent carry 4 to 5% Denisovan DNA. These weren't separate species in the strictest sense. They could have children together, fertile children, who survived and passed on their genes. Perhaps species is the wrong word entirely. Perhaps they were lineages, branches of a broader human family, each adapted to different corners of the world. The story emerging from fossils and DNA is messier than the old textbooks suggested. Humans left Africa in multiple waves. Some migrations succeeded for a time, then faded. Some groups interbred with archaic populations. Some returned to Africa. Climate pulses, periods when the Sahara greened up due to orbital cycles, created corridors that opened and closed like valves. Around 70,000 years ago, something changed. What made the final wave of humans out of Africa different? Not technology, necessarily. The sophisticated tools that later appeared in Europe, bone needles, atlatls, elaborate blade production, didn't emerge until after Homo sapiens had already spread across the world. Not bigger brains. Neanderthals had large brains. They had fire, clothing, burials, probably language. The difference, according to research published in Nature in 2025, was ecological flexibility. Between 70,000 and 50,000 years ago, just before the major successful expansion, something unusual appears in the African archaeological record. Humans start occupying a much wider range of environments within Africa. Dense forests, arid deserts, coastal zones, alpine highlands. This is new. Earlier populations tended to stick to familiar habitat types, but these late Pleistocene Africans were experimenting. learning to thrive in forests and deserts, mastering coastal resources, shellfish, marine mammals, seabirds, developing technologies and knowledge systems flexible enough to work in radically different environments. And then they left. By 65,000 to 50,000 years ago, Homo sapiens had reached Australia, a journey requiring seafaring. By 45,000 years ago, they were in Europe. By 40,000 years ago, deep into Asia. By 15,000 years ago, they'd crossed into the Americas. From the ice fields of northern Europe to the jungles of Southeast Asia to the frozen Bering Land Bridge, Homo sapiens spread into every terrestrial environment on Earth. Not because we were adapted to ice or jungle or grassland, because we could adapt to anything. The Neanderthals held on for a long time. Isolated populations survived in mountain refuges in Croatia, the Iberian Peninsula, the Crimea. The last Neanderthals died out around 40,000 to 28,000 years ago. Homo floresiensis may have survived on the island of Flores until as recently as 50,000 years ago. We don't know exactly why they disappeared. Competition with Homo sapiens? Climate change? Disease? Absorption through interbreeding? Perhaps all of these. But here's what we do know. By 28,000 years ago, the diversity was gone. The other branches of the human tree had ended. Only one lineage remained. Ours. The descendants of those African populations who learned to thrive in chaos, who adapted not to one environment, but to the principle of change itself. We are alone now, the last humans. And that aloneness carries weight, because for the first time in millions of years, we are the only hominin species on Earth. There is no one like us, and no one to compare ourselves to. Our adaptability brought us to every corner of the planet. The question now is whether that same adaptability is enough for what comes next. Let's return to where we began. To climate. To change. For 3 million years, our ancestors evolved in Africa while the climate oscillated. Ice ages came and went, rainfall patterns shifted, ecosystems transformed. And generation after generation, the versatilists survived while the specialists died out. Adaptability was the answer. The ability to change your diet, your tools, your strategies, your locations as the world shifted beneath your feet. But adaptability comes in two forms. There's biological adaptability, the kind that emerges over thousands of generations through genetic variation and natural selection. This is what gave us our large brains, our flexible shoulders, our capacity for learning. And there's cultural adaptability, the kind that happens within a single lifetime through knowledge, innovation, and technology. Somewhere along the way, our ancestors made a profound transition. They stopped waiting for their genes to solve problems and started solving problems themselves. Tools, fire, clothing, shelters, language to share knowledge across generations. Social structures that allowed specialization within groups. These weren't just technologies, they were a new form of adaptation. Faster than genetics, flexible within a single lifetime. And here's where the paradox emerges. For millions of years, climate change was the engine of human evolution. It forced us to become adaptable, to innovate, to cooperate across distances, to think symbolically and plan for uncertain futures. Climate change made us human. But the adaptability it gave us, particularly our cultural, technological adaptability, changed the equation. Because now, for the first time in Earth's history, one species has the power to change the climate itself. Geologists debate when to mark the beginning of the Anthropocene, the age of humans. Some point to the invention of agriculture 10,000 years ago, when humans first began reshaping landscapes on a massive scale. Others point to the Industrial Revolution in the 1800s. Still others suggest the mid-20th century, when radioactive isotopes from nuclear testing spread across the globe. Rick Potts has a different answer. The Anthropocene, he suggests, began 2.6 million years ago with the first stone tools. The moment humans started deliberately reshaping the world rather than merely living in it. That power has escalated. Humans now control 6 times more fresh water than flows freely across continents. 83% of all viable land is occupied, used, or altered by humans. The chemistry of the oceans is changing from agricultural runoff and carbon absorption. The composition of the atmosphere has shifted more in the last 200 years than in the previous 10,000. We are, quite literally, a geological force. The same cognitive flexibility that allowed our ancestors to survive ice ages and droughts has created technologies that alter the planet. Agriculture feeds billions, but transforms ecosystems. Fossil fuels power civilization, but change atmospheric chemistry. Medicine extends lifespans, but grows populations beyond historical bounds. We evolved to reshape our immediate environment to suit our needs. That's what made us successful. Every tool, every fire, every shelter, every irrigated field, that's adaptability in action. But the environment we're reshaping now isn't immediate. It's global. It's atmospheric. It operates on timescales longer than human lifetimes, making the feedback invisible until the consequences are profound. Cultural anthropologist Tim Waring puts it starkly. The process of cultural adaptation to the environment, what made us successful, may obstruct global solutions. We are wired to solve local problems with local innovations, but climate change isn't local. It's a systems-level challenge that requires coordination across nations, cultures, generations. Can a species that evolved for adaptability adapt to the consequences of its own success?
There's an argument some people make, that humans are somehow separate from nature, that our technological power makes us different from other species, that we've transcended our evolutionary origins. That's wrong. Study evolution, and the boundary between humans and nature dissolves. We are not separate from the natural world. We are nature, becoming conscious of itself. Every behavior, every tool, every piece of culture, it all flows from the same evolutionary process that shaped every other living thing. We're not exempt from ecological laws. We're subject to them, profoundly. But here's what evolution actually teaches us. We come from survivors. When the climate swung from wet to dry to wet again at Olorgesailie, some populations died out. Others persisted. The ones who persisted were the ones who could adjust, who could learn, who could cooperate across groups to share resources and information. We are the descendants of those people. Every human alive today carries genes from ancestors who survived drought, ice ages, volcanic winters, disease pandemics, predators and competitors. Not because they were the strongest, not because they were perfectly adapted to any one environment, because they could figure things out. Together. That capacity didn't disappear. It's in us. The same brains that allowed our ancestors to survive climate chaos are the brains we have now. So here we are, the most adaptable species Earth has ever produced, facing the consequences of that adaptability. The climate is changing again, not over hundreds of thousands of years this time, but over decades. Not from orbital wobbles or ice sheet dynamics, but from our own activity. Carbon dioxide levels are higher than they've been in 3 million years. Global temperatures are rising faster than any period in the past 10,000 years. The question is not whether we can adapt. Our ancestors adapted to far worse: ice ages, volcanic winters, the complete collapse of familiar ecosystems. The question is whether we will choose to adapt consciously. Our ancestors didn't decide to evolve bigger brains or more complex social structures. Those changes emerged over thousands of generations through selection. They were passive recipients of evolutionary forces. We have a different option. We can see what's coming. We can measure it, model it, communicate it across the entire species instantaneously. We can develop technologies that don't just help us survive change, but prevent the worst of it. We can coordinate action across nations. We can plan not just for our own lifetimes, but for our grandchildren's grandchildren. This is unprecedented in Earth's history. A species with the capacity to consciously direct its own future. Will we use it? The answer isn't certain. Cultural evolution is slow. Political systems are fragmented. The same tribal instincts that helped our ancestors survive in small groups now divide us into competing nations. The same short-term thinking that got our ancestors through the next season makes it hard to plan for 2050, let alone 2100. But
we've done impossible things before. We crossed oceans on rafts. We settled every continent. We built cities, languages, art, science, medicine. We sent humans to the moon and robots to Mars. We decoded our own genome. We connected the entire species through a global network of information. We are the descendants of climate survivors. Adaptability is what we are. The story of human evolution is not a story of strength or perfection. It's a story of flexibility, of innovation under pressure, of cooperation when it mattered most. We are here because our ancestors faced chaos and figured it out. The planet is changing. It has changed before, and it will change again. The question is not whether humans can adapt, it's whether we will. Whether we'll look at the data and make choices that extend beyond ourselves. Whether we'll cooperate across tribes and nations. Whether we'll use the same cognitive gifts that got us here to navigate what comes next. Our ancestors didn't know they were evolving. They were just trying to survive. We know. What we do with that knowledge, that's the story still being written.
This is Cosmic Canvas, where we trace the forces that made us human. Until next time, remember that climate change created us. Now we must decide if we can survive what we've created.